Okay, yeah, my name is Lasse, and yeah, I work for TimeBeat. We're a company in the UK. We do some very cool, like servos and for PTP and so on. And we've developed a particular thing which is a little unconventional called PTP squared, and in this presentation I'm going to talk about it. So firstly, this is my 1588 PTP is a great achievement. Okay, I pat the entire industry in the back and say that it's great. It's a great achievement. Okay, with the hardware support, it gives good accuracy, blah blah blah, and it has real uses, right? In finance, it prevents things like front running by allowing sort of accurate sequencing of things. However, okay, there are a few things I don't like about it, and now we're going to talk about them. Okay, so the first is this, right? This is like the classic sort of PTP sort of setup, right? You have a grandmaster somewhere, you have some boundary clocks, and then the OCs, there's some servers, right? And the issue I have with this whole architecture is that every single green thing in this diagram is a single point of failure, right? If the grandmaster has the wrong time, it gets propagated downstream, right? And if a boundary clock does not work, everything downstream, it doesn't work, right? Even like in the links between them. I don't know if you've ever had like an SFP connected with another SFP. If the two SFPs are different, you introduce an asymmetry, right? And there's no way to find this out because everything has just a single parent, right? So it's like you're walking down the street, you say to a guy, what time is it? And he says it's 3 o'clock. You're going to have to take his word for it if you can't ask more than that guy. Okay, and so what we see is that that in the real world, right, when we go out somewhere and they have this setup, right, we connect to two servers somewhere, and then we check, okay, but if you actually look at, do they have the same time? Very frequently, the answer is no, they don't, right? And it's sort of like as we moved in terms of accuracy from milliseconds to microseconds, nanoseconds, and now with some technologies, picoseconds, it's like our strategies remain the same, and what used to be like insignificant sources of errors, they're now sort of more significant. So there you go. Oh yeah, and then as I say here, also like the concept of best master clock, right, is somehow profoundly flawed, right? Like the idea that a source of time tells everyone, oh, I'm the best. It doesn't have to be the case, like on the other side of a link or infrastructure, right? It's sort of it's not real. Okay. So here comes some very advanced PowerPoint action, okay? So I wanted to draw this parallel, okay? And we come from London, and if you ever visit, right, you should go and see the Royal Observatory in Greenwich. It's nice, okay? There's my daughter, and you can sort of see the area, okay? That's the Royal Observatory there, where the red thing is, and you see the park around it, okay? It gave me inspiration. If we take it out, okay, get ready for this. Come on, wait. Now what's the final? Okay, there we go. So this is what I want, right? Here we have a mesh of things, okay, with lots of interconnected paths, okay? If you're a clock here, you can talk to other clocks through lots of paths. You don't have this single parent, single source relationship, okay? And throughout this mesh, if we think about it in the data center context, every consumer of time should also be a provider of time, okay? But how? So we think again about the old model, okay, which I don't like, and then we turn it on its head, okay? Right. So what we have here, okay, is what we've done with what we call PTP squared, okay? And I'll show you in the next couple of slides how it works. But just the principle is that if we look at the server, which is on the right here, upstream from it is many paths, okay? So time can come, via A, E, G, or it can come via C, F, G, and you can imagine how, you see how it says times n in the corner there, you can imagine how it has many upstream paths, okay? And so this is how we've done it, and we've built sort of a distributed hash table system that creates this network of paths, this directed acyclic graph dynamically, so you don't have to configure it statically, and then we have a system where paths are selected based on the cumulative variance. Okay, so if one server via path A is sending time to sort of the server you see there in the middle, okay, the offset distribution is going to give rise to some variance, right? So between each server, there's going to be an offset distribution with a variance, and as we proceed down through a path, we add, let's say, the variance, which is upstream hop by hop, and then we can say something about what's the total error by the time we get to, let's say, the last hop in the path, right? And the benefit of that is that if you have congestion somewhere in the network, right, you can imagine that upstream in a particular path, all of a sudden there's someone downloads a large file or whatever the case may be, okay, immediately that path becomes associated with a higher cumulative error, and then nodes downstream can just decide to take synchronization from another path, right? In fact, they can decide to take synchronization from many paths, right? Which is cool. So ultimately, a server sees many paths, okay, each which gives rise to one amount of cumulative variance and has a particular offset in relation to the server's own clock, and you get sort of a Gaussian distribution of offsets. And then, if somewhere in the network somebody thinks it's 1982, you can just ignore them, right? This you cannot do with the standard model. Okay, and so if you turn this on in a network, okay, this was like for LinkedIn, so we gave all of the servers silly names, and I think there's a special focus on Moscow, which is not so good in the present circumstances. But here you can sort of see, this is something we built with D3, and here you can sort of see as we hold the cursor over different of these nodes in the squared grid, you can see that the red sort of paths are what is incoming in terms of time to that server, and the blue ones is what's sort of outgoing from that server. So it both receives time from a set of servers and it gives time to a set of other servers. And then, and then some of the paths, the line is solid. So it indicates that that path is actually being used for synchronization, and some of them are sort of with dotted lines, and this indicates that they're sort of on standby. So if a server decides to use another path, it can switch quickly over to that, and all of the filters are preloaded with information which allows accurate synchronization by understanding path delay. And you can also, because it's just PTP, right? Essentially, these are all just PTP unicast sessions between nodes, and then there's an overlay network that sort of establishes the mesh. But because it's just PTP, you can run high rates of exchanges across the paths that are being used for synchronization, and you can then have more conservative usage for those that are just being monitored. Okay, and then here's how we do This is like for monitoring, the quality of time, you could say. So every node is a bubble, right? And then depending on, and here we're running it faster, right? But it's the same network. And so every node has these several paths. Right here you can see that I think every node here has 3 paths. And depending on what is the cumulative error of the path that it's using for synchronization, we color the bubble green or yellow and red, and it's running on repeat, right? And what we're seeing here is actually like a network which is converging, and so you can sort of see how, as it transitions from a lot of red and yellow bubbles to green, the quality of synchronization becomes better, right? It converges. Okay, and hybrid approaches are welcome, right? So it means that you don't have to, if you like this system, right, and you think, wow, this sounds kind of cool, what you can do initially is, if you have the traditional boundary clock infrastructure, you can just run PTP squared and create this mesh between servers for monitoring purposes, right? So you can install our software, and by the way, it doesn't cost anything. You go onto our website and get it for free. And then you can install it on your servers, and you can allow them to speak with each other in a monitoring-only capacity. So you can have standard PTP for synchronizing your clocks, but you can have your servers talking to each other so that you get a sense for, does the time on this server compare with the time on these 3 other servers? Okay, and if the answer is no, then you probably have a problem somewhere, and it's worth paying attention to that. And then we did some hardware, right? So we worked for Raspberry Pi, okay, to put the 1588 capability in the CM4, okay. So Broadcom was involved and Raspberry Pi, and then we had now all of a sudden hardware timestamping capabilities in the compute module 4, which is cool. So we thought, now we got to build a cool receiver for it, so we didn't want to tie up the 40-pin connector, right? So we had this board built, okay, we call it the sandwich board, so it sits in between the CM4 and the CM4 I/O board, and you can have it with a u-blox Leah or a Max, so it can provide very good time, and we're working with SciTime, right, to put one of the high-quality MEMS oscillators. You see the little module A and B in the bottom of the big guy there. We put this this little board here. You can put it on there, so it gives a very good holdover capability. Right there, oscillators are enormously cool, down to 5 parts per billion. So so that's kind of cool. And here's some other stuff we do. Okay, we manufacture and sell the time card. We have a portfolio of clocks. Okay, some are based. You can see the little one in the middle. That's actually based on the CM4. The larger ones, we put a GPS DO inside a PC, and then it runs our software. So these are sort of ideal. The small one is good for like verification things. The larger ones are good for injecting time into a squared network or in the traditional grandmaster type role. Right? Okay, so you should definitely get involved with OCP-TAP if you're interested in time. Okay, I call it the Woodstock of clock synchronization. Okay, I know a few other fora that has people that are willing to think differently and do interesting things. So I like it for that. You can have a look at our store, the things that we sell, and there's some links with more resources. So that's it. If you have any questions, let me know.
Thank you, Lasse. Any questions, guys?
Well, thanks for the great talk. I'm really very impressed about the idea. But my question is, when you have the mesh comparison, how do you decide which one to sort of follow? Or are you going to adjust to the average of the mesh network, or how do you sort of pick the right frequency and time?
Yeah, that's a good question. So we don't take the average because then it would be not the sort of then outliers would you know. So typically we go for the median, but there are other strategies as well. Yeah, sorry, it's so cold in here. I feel like
You
a frozen
think?
chicken.
I didn't notice anything about it.
So it's basically, I mean, some weighted average in a sense that you will throw away outliers.
Yeah, what I can tell you today is that it is a proprietary algorithm, is what I'm prepared to tell you. Yeah.
Okay.
But it is, let's say, a cooperating clock where you take time from multiple sources and you synthesize essentially what you think the time is. But it's remarkably accurate.
From experience, we recommend taking it for a spin. The results are amazing. So thank you, Lasse, for agreeing to present this year.
Yeah, it's okay. It was a mere 10,000 kilometers from where I live. So.
Hence I asked.